So we've got this function, f of x is equal to negative quantity x minus 3 whole thing squared plus 1. So if we do this the way that we were doing it in here yesterday, this is already in our vertex form, so we can read off the vertex from this. So I know that my vertex is going to be at 3, 1. And just as a quick reminder, if it's already in this completed square form, then whatever makes the part in parentheses equal to 0, that's the x value of our vertex. And when you plug that in, whatever answer overall you get, that's the y value at the vertex. So now I've got my vertex. And then if we wanted to find the x-intercepts, I'm going to find those x-intercepts by setting y equal to 0. So if I set y equal to 0, then I'm going to have 0 is equal to negative x minus 3 squared plus 1. So I can take that whole thing and add it to the other side so that I've got x minus 3 squared is equal to 1. And I know I'm doing this differently than what I did the other day, but again, it's kind of all about options. We can just take the square root of both sides. As long as we remember that when we take the square root of both sides, we're going to end up with either a positive 1 or a negative 1. So I'm going to, if we take the square root, we're going to get that x minus 3 is equal to plus or minus 1. So kind of thinking back to our section on solving equations with radicals, this is kind of like squaring both sides, but instead of squaring both sides, I'm raising both sides to the 1/2 power or taking the square root of both sides. So if I think it's easier to actually write this out as two separate equations and say x minus 3 is equal to positive 1 and x minus 3 is equal to negative 1. And if we do that, I'm going to end up with x equals 2 or x equals, I can't really add things today, huh? 1 plus 3 is actually 4. Fun fact. And if I add 3 over here, I'm going to be at 1, right? Negative, no, 2. Seriously, I'm having an arithmetic failure this morning. So I'm really going to keep an eye on the chat, and you all are going to have to call me on it when I'm making some dumb arithmetic moves. Okay. I'm going to pause for a second because there's a particular reason that I caught my mistake just now. And the reason that I caught my mistake is that the vertex, the x value of the vertex, should always be exactly in between the two x-intercepts. If you have two x-intercepts, we don't always have two x-intercepts, but if we have two x-intercepts, then the vertex should always be exactly in the middle. So when I wrote 4 and 1, I was like, oh wait, 4 and 1 doesn't make sense. 3 is not exactly in the middle of those two. I think it's good to be able to catch your own mistakes, so I figured I'd point it out. Okay, so putting the points that we know on our graph, so we've got x-intercepts at 2 and 4, and we know that our vertex is at 3, 1. And that's probably enough for you to kind of see the shape of the graph going already, but there is one other critical aspect here, and that is that our value of A, or that number out there in front, is negative, which means that this parabola is going to be concave down. Good times. Questions about my lovely parabola? Oh yeah, so what's the y-intercept? Totally, James was probably making you find y-intercepts. Okay, so the y-intercept usually is easier to find than the x-intercept, because when I find the y-intercept, that's always happening from setting x equal to 0. So if I plug in 0 for x in the equation, and I don't have a ton of space, so I'm going to do it down here, but when I plug in 0 for x in the equation, I have 0 minus 3, whole thing squared, make it negative, add 1. So 0 minus 3 squared, that's going to give me negative 3, square it, it will be positive 9, but the negative out in front will make it negative. So I'm at negative 9 plus 1. So if I kept this going, my intercept would be at 0, negative 8. I'm going to let you in on a little secret. It's not really much of a secret. When you get to calculus, no one's going to ask you to graph a parabola. What is going to be expected of you is that if we have the equation, let's say y equals x minus 3 times x plus 2. In calculus, I'm not going to ask you to graph this and show me the intercepts and find the vertex and any of that. But I expect you to look at that and not think too hard and be able to sketch a quick graph and go, oh yeah, the intercepts are at 3, negative 2 opens up. That's what I expect you to be able to do quickly in calculus. Now, the other thing that's going to be expected of you in calculus is to look at this equation or this graph and say, what's the lowest point down here on the graph? And that lowest point, we call the vertex, and you have to know at least one method for finding the vertex. And I think James showed you yesterday that one method for finding the vertex is that our x value for the vertex is negative b over 2a. Another way to find the vertex is to complete the square so that you have the vertex form of the parabola, and our vertex has coordinates hk. And I mentioned a third option for finding the vertex, which is, it's the average of the x-intercepts. So which method I use to find the vertex depends on which equation form the parabola is in. So one of the things that is true about me is I was never the person that had extra, I was using every second someone gave me to finish a test. I feel like I don't write very quickly, and I definitely do not think well on my feet. Right? So I don't think well under pressure. So I had to get smart about recognizing what strategy was going to help me get through a problem faster. So I would use finding the average of the intercepts if the parabola was given to me already in factored form, or if I could factor it quickly. So this thing is already factored for me. So I would be going with average of the x-intercepts. On this one, I would say that my x value at the vertex is negative 2 plus 3 all over 2, because that's how you find an average. You add the two numbers, you divide by 2. If I was finding the average of 17 numbers, I'd add them all up and divide by 17. But here, I know that that x value at the vertex is 1/2. And now I just have to find the y value when I plug in 1/2. The other nice thing, because Davis is not a calculator school for calculus, you don't really have to finish the math off. My y value at the vertex would look like 1/2 minus 3 times 1/2 plus 2. Could you finish that number off? Yes. Should you, if you're doing homework? Absolutely. Grab a calculator, finish that off. But if this were a test, I'm done. That's my vertex. Now, if the question is given to me, let's do another example, right, from our 3 different vertex forms. So if I gave us y equals negative 3x squared plus 2x plus 5, we could factor it, we could complete the square, but if neither of those look good to do, I'm going to use negative b over 2a. So if I look at this, I don't know, does it factor? Here's what I'm going to say. If you can't see how it factors within about 30 seconds, move on with your life. So if I can't see how that factors in about 30 seconds, I'm almost never going to choose to complete the square if there's a number coefficient on the x squared that I can't factor out from everything. Because for sure I know that's leading to fractions. So I'm going to look at this and say, oh, if I need to find the vertex, I am going negative b over 2a. Here's my b. Here's my a. B is positive 2, a is negative 3. So my vertex here for negative b over 2a is going to look like negative 2 over 2 times negative 3. You're welcome to cross out those 2's if you like, as long as you remember that that's going to leave us a negative 1 on the top. So I'd have a negative 1 over negative 3 or positive 1/3. Now, once you find the x value of the vertex, you still have to go back and figure out the y value. The one advantage of completing the square is you get both at the same time. You get the x value and you get the y value. But if we're not worrying too much about doing the calculations ourselves, I'll just go ahead and plug in the 1/3 everywhere we have an x. And like I said yesterday, given time, energy, and sufficient monetary motivation, you could turn that into a number. All of you could. I have faith. If we're handed a parabola that already beautifully is in our vertex form. Oh, wait, hey, we should graph this thing, right? We should at least do our quick calculus style sketch of this thing. Now, I said that it didn't have to be that pretty, but it has to be roughly accurate. So how would I do that if I didn't want to work out what this value was for the vertex? Well, I know that the x value is 1/3, which means my vertex is going to be somewhere over here. I can find the y-intercept pretty quickly because my y-intercept is going to come from setting x equal to 0. So my y-intercept is going to be 5. And I know that because the a is negative, this has to be concave down. So this is the part where I'm going to ask you to be brave. I can't even see your paper. So I just want you on your paper Don't figure out what this number is. I want you knowing only that this is the y-intercept, the x value of the vertex is 1/3, and this thing is concave down. Give me a quick sketch of what that parabola has to look like. I told you, I can't even see your paper. Low risk. Okay, I'm going to show you mine. There's the intercept. If it's going to be concave down and the vertex is over here, it can't look like this. It has to look like this. Justin wants to fence 3 sides of a rectangular exercise yard for his dog. The 4th side of the exercise yard will be a side of the house. He has 80 feet of fencing available. Find the dimensions of the exercise yard that will enclose the maximum area. Like I do, oh yeah, this is the last part of class T. It's the last question on part T. Like I do with other word problems, I start at the end and I work backwards in that sentence or clause until I find the question-y word, the instruction-y word. Area maximum, the enclose, will, that, yard, exercise, the, of, dimensions, the, find. Okay. What are we supposed to find? Dimensions of the exercise yard. So we're trying to find dimensions. And so if I'm trying to find dimensions, then I'm kind of looking through the problem again and saying, well, what is this thing? It's rectangular. So if I'm trying to find the dimensions and I know it's rectangular, then this is asking me either for the base and the height or the length and the width. Doesn't matter which one you like better. But that's what my dimensions are going to be. What's the length and the width? Now I'm looking for more information in the problem. Personally, I'm probably drawing a picture. You might be able to do this without a picture. I like pictures. So I'm going to start just trying to get a grasp on what we've got going on. We're going to fence 3 sides of a rectangular exercise yard. So here's my rectangle. And I'm going to call this the width and the length, which means since it's a rectangle, this side is also the width and this side is also the length. But the 4th side will be the side of a house. Okay, so there's like house over here. He has 80 feet of fencing available. And we're trying to find the dimensions of the exercise yard that will enclose the maximum area. So this maximum area thing, anytime we're trying to maximize, minimize, shortest, fastest, longest, quietest, anything ending in ist, we're probably doing some kind of optimization problem. An optimization problem just means we're probably going to have some sort of parabola thing, and we probably need to figure out either the smallest value or the largest value. And once we have calculus tools, it doesn't always have to be a parabola, but that same idea is going to hold. We're looking for places where we're like at the top of a graph or where we're at the bottom of a graph. For right now, they should all work out to be parabolas if we're being asked to maximize or minimize. So if I'm trying to maximize the area, really the first thing I need to do is to figure out a formula for the area. And when I write this down, I'm going to have area is equal to the length times the width, or L times W. And then I look at that and I say, oh darn, I have two variables. I only know how to graph parabolas if they say something like y equals x squared plus an x plus a number. I don't know how to graph parabolas with L's and W's floating around in there. I sure hope we know something else about the problem. And if we scan through the problem quickly, there's another number that's popping out of the problem, and that's that 80 feet. So 80 feet of fencing, sometimes we call that our constraint. Sometimes you might hear it as a helper. But that 80 feet of fencing, now I've got to think in context, what does that 80 feet really mean? Well, if this is my rectangular exercise yard, then that fencing has to go this whole length W, or that whole width W, plus this length L, plus this width down here. So that 80 feet of fencing has to be equal to W plus L plus another W to get all the way around those three sides. Well, now this equation, I can move over here and say, okay, well, I can rewrite that as 80 is equal to 2W plus L. Sorry, covered it up with my picture. 2W plus L. And I can rearrange this to say L is equal to 80 minus 2W. The reason that's helpful is now if I come over and look at my area equation, but I replace L with 80 minus 2W, then I can say that my area is equal to 80 minus 2W times W. And even though that might not look like the equation of a parabola, if I were to call my A Y and I were to call my W X, it is the equation of a parabola in factored form. Now, why is that helpful? 80, thank you. Thank you. See, told you, wasn't going well today. Appreciate the chat. So why is this helpful? We're trying to find the largest area. So if I know what this graph looks like, and personally, I do know what this graph looks like. If I know what this graph looks like, I can put my X value or the width down here on this axis, and I can put the Y value or the area here on this axis. And if I sketch this, I know that the vertex of this parabola is going to show me that maximum area. Well, this is already in factored form. Since it's in factored form, I'm going to say, hey, I know what the x-intercepts are. My x-intercepts are going to come from 80 minus 2x is equal to 0 and x is equal to 0. So what's that, 40? There are two reasons that I know this parabola has to be concave down. The first is it asked for the maximum area, so it has to be concave down. The second reason I know it's concave down is that if we multiplied this out, the coefficient on the x squared term would be -2. So that would also tell me that it's concave down. Because this thing was already factored for me, I'm going to say, I know the x value of the vertex is going to be the average of the two intercepts. So the x value of the vertex here would be 20. Oh, I don't know why I already closed those parentheses. The x value of my vertex would be 20. And the y value of the vertex would be whatever we get when we plug 20 back in. So if I plug 20 in here, 2 times 20, that's 40. 80 minus 40 is 40. 40 times 20 is 800. 40 times 20, yeah. That just told me that the maximum area is 800. And we get that maximum area when the width is 20 feet. Oh yeah, good point. My graph, guess what? It is to scale. You know why it's to scale? I didn't use graph paper. Because I didn't use graph paper, labeling this point 20, 800 defined what the scale of my graph is. Now it's not a 1-to-1 scale, but it actually is to scale. So if this is 800, that would make halfway here 400, and halfway there 200, and halfway there 600. So it is scaled. It's just not a 1-to-1 scale. I was working on my garden plan the other day and decided that I want a rectangular planting bed in one corner of the garden. I want that edge typo to touch a path. So I figured out that the width of the planter W is related to the length L by the equation L equals 12 minus 3W. The area of the planter box is area equals width times length. So I've already given us the helper equation this time. So when I say to write the area as a function of just W, that means that I'm taking that area equation and doing kind of what we did on the previous one, where instead of writing it as W times L, I want to write it as W times the equation for L. So I'll have W times 12 minus 3W. Now, notation-wise, we can say that this is A, and then in parentheses, put a W. And when we read this as A as a function of W. And what that means is that the area will only depend, the only thing we will need to know in order to find the area is the value of W. That's what this notation means. So we call this function notation. It does not mean A times W, which is confusing because usually parentheses mean we're multiplying things. But when we write it in this way, and when we're looking at something written in this form, we kind of have to deduce from the context of the problem whether that means that I'm doing A times W or if it means A as a function of W. Yeah, just like when we write f of x. So if we write f of x, that notation means f is a function of x. And we could just read that as f of x, and I could read this as A of W. But the underlying thing behind it is to say this is only a function of W. Just as a side note, if I was looking at area equals W times L, then another notation that I could use is area, and then in parentheses, I could put W comma L. And this would imply that in order to find the area, I would need to know the values of both W and L. So we would say A as a function of W and L. And we'll have a bunch of stuff like this when you get to third quarter calculus, whether it's 16A, 17A, or 21A. Third quarter calculus will start to talk about things that look like this. But for now, that's a long way off. Focus on the problem at hand. So first thing that I'm asking us to do is sketch a graph where area is the y-axis and width is the x-axis. So if you want, you can go ahead and even just switch the variables like that. So if we switch the variables to make it say y is equal to x times 12 minus 3x, I'm going to give you all a couple minutes to sketch a graph of that. Doesn't have to look perfect, but yeah, doesn't have to look perfect, but get a quick sketch going for that. Not sure if people want more time than that. I'll talk kind of slowly. No. So just, we have three options for finding the vertex. If I'm going to sketch it personally, especially if I know that really what I'm aiming for is figuring out the largest possible area, if I'm like looking ahead in the problem and I know that's where I'm going, I know I'm going to need the vertex. So the x-intercepts in the vertex, that's going to be enough to get me a graph. So my x-intercepts here, I'm looking at x equals 0, x equals 4. And whichever way you want to find the vertex, it's either the number in between 0 and 4, the average of 0 and 4, which is 2, or you can get it by doing negative b over 2a. So I did go ahead and multiply this out and put it in the standard order so that we can get that a is negative 3, b is equal to 12. And if you wanted to think about that vertex as negative b over 2a, that's also going to get us to a value of 2. So either way, I've got my x-intercepts and the x value of my vertex. So I've got intercepts at 0 and 4. And I'm going to go ahead and label my axes here just to remember that this one's the width and this one is the area. Draw in my parabola and we'll label the vertex up here. We know that the x value is 2. And to find the area, we can choose any of these versions of the equation to plug it in, but I'll go with the factored form. So 12 minus 3 times 2, 3 times 2 is 6. 12 minus 6 is also 6, and 6 times 2 would get me to 12. So there's my quick sketch. By the way, we did also find the y-intercept because it happens to be 0. So now I'm thinking about what is the largest possible area according to the graph. Since I labeled my vertical axis here as the area, I can pretty quickly see that 12 is the largest area, but then I'm going to have to go back and read the problem to remember what kind of units we should have. Cool. I didn't give us units. Good times. Well, we could pretend we had units and then it was feet. And then because it's area, it would be square feet. Or if I had a teeny tiny planter bed, it might be 12 square inches. Or if I had a really huge one, it could be 12 square meters. But either way, by the way, this is actually the one that's more realistic for my yard. But the thing I'm pointing out is that whatever the units are, if it's area, the units should be squared. Yeah, so why are the units squared when we talk about area? So if I take this thing and that's 3 feet by 4 feet, which would give me a 12. If that's 3 feet by 4 feet, then when I multiply those together to get the area, I'm literally multiplying 3 feet times 4 feet. So the 3 times 4 gives me 12, and feet times feet, we write like that. Next part of this question, find the length and the width that the planter box should be to have this largest area. So my width here is coming from my horizontal axis. So to get to that largest area, the width that we are at is 2. So this would be a width of, let's say, 2 feet. And then if I want to find the length, I'm going back up to the original equation somewhere to find something that says length equals. And here it is. There's my length equals. Since length equals 12 minus 3 times the width, I know that my length is going to be 12 minus 3 times the 2 feet, or 6 feet. From a calculus textbook. So specifically from the Calc for Biosci textbook, the growth rate G for a certain plant is a function of the amount of phosphorus in milligrams in the soil, as well as a function of the amount of nitrogen in milligrams. The amounts of nitrogen and phosphorus vary over time, T in hours, and I read this as N of T, or nitrogen as a function of time, is equal to 3 plus 2T, and phosphorus as a function of time is equal to 8 minus 3T, respectively. If the growth rate is N of T times P of T, express the growth rate as just a function of time. That's a whole lot of words that aren't really telling us to do much. This is just saying we're going to write that growth rate not as N of T times P of T, but replacing the functions for N of T and P of T. Two T. Thank you. Thank you. I think I was seeing it at the same time. Okay. At what times will the growth rate be 0? Question mark, working backwards, found the question word, what times? So I know we're looking for a value of time when the growth rate is 0. And that growth rate of 0 means G is equal to 0. So even though it's not exactly an x-intercept, it is really an x-intercept. It's just this time we have different variables in there. We're talking about t for time. So at what times will the growth rate be 0? If I have two things multiplied together to be equal to 0, one of those two things must be equal to 0. 3 plus 2t equals to 0 means 2t is -3 and t is -3/2. Or if 8 minus 3t is equal to 0, 8 is equal to 3t, t is equal to 8/3. Now I'm about to say a terrible math joke. You can have a good time, you can have a bad time, but you can't have a negative time. No one yet has figured out time travel. So in terms of answering the question, at what times will the growth rate be 0? We can't go back in time. So in the context of this problem, my only answer would be 8/3. Even though both of these are the solution to the equation, and they're both valid solutions to the equation, when we have word problems, we also have to take into account the context of the word problem to see if the solutions are reasonable. And here, a negative time isn't reasonable. So the only answer to that second question would be that t equals 8/3. Now part C, at what time will the growth rate be largest? So we could sketch a graph, or we can just think generally about what's going to happen when we do sketch that graph. So if I'm trying to figure out when the growth rate is largest, first of all, I know it's quadratic. If I'm looking for the largest, it must be concave down. And if I'm trying to find the largest, I'm looking for where that vertex is. Now, if I were labeling the axes, well, I don't actually know where the axis goes, but I know that this axis would be time, and the other one would be our growth rate. So if I want to know that at what time, I'm really thinking about essentially what's the vertex? What's the x value at the vertex? Or in this case, the t value at the vertex. You've got choices. You can multiply that out to do negative b over 2a. But since we already know what the two intercepts would be, I would find it by taking the average of those two numbers. So I would find my t value for the vertex by doing -3/2 plus 8/3 all divided by 2. Look at that. I found a way for us to practice common denominators. How'd I do? Did I get the same thing other people got? Oh, there's a question in the chat. Yes, you could have just multiplied the top and the bottom of the original fraction by 6 to get rid of all the denominators entirely. That would totally work, and you should have still ended up with the same answer of 7/12 at the end if you did it that way. So I chose to get a common denominator in the top and then combine those together as a single fraction, and then to switch dividing by 2 to change that into multiplying by the reciprocal or multiplying by 1/2. Let's kind of dissect this word problem a little bit. And the first thing that we're going to need to understand here is we're supposed to write a quadratic function that models p as a function of x. So p is not the price in this problem. P is the demand. And the demand, we're told, is in thousands of boxes sold. So we're looking for like boxes sold is equal to something that involves x, and x is the price. Some function of price. Now we're told that this relationship is quadratic. So we actually have a couple of options for how to approach that quadratic, right? I know it's quadratic, so I could think about it as ax squared plus bx plus c. And that would be a decent option. Now looking at this, if I wanted to actually come up with the equation, I would need to know a, b, and c. And if I have 3 unknowns, I would need 3 pieces of information in the problem. But we were not given 3 pieces of information in the problem. We were actually only given 2 pieces of information in the problem. That at $5 per box, we sell no boxes, and we sell the maximum number of boxes, 9,000, when they charge $2 per box. So instead of thinking about this version of the quadratic, I'm going to take advantage of the fact that it says maximum to say, oh, well, I'm just going to go straight to the vertex form for the equation of the parabola. A is equal to x minus h whole thing squared plus k. Because we know what the vertex is. We know that when we charge $2 per box, so here our vertex would be h comma k. And in this statement of the problem, we know that when we charge $2, we sell 9,000 boxes. And there is a note to be careful about the units because it says P in thousands. So rather than 2 comma 9,000, this would just be 2 comma 9. So now I know in the equation, I'd have P is equal to A times x minus 2 whole thing squared plus 9. And to solve for A, we're going to need another piece of information. And that is the fact that they sold that at $5 per box, they sell 0 boxes of cereal. So the demand is equal to 0 when x is equal to 5. And that should be enough to let us solve for the value of A. I know I'm out of time. If anybody needs to go, please leave. But I am going to finish it off at least. So let me clear my highlights so weird things don't happen when I move it. So I know the demand is 0 when x is equal to 5. And plugging that in, I've got 0 is equal to A times 5 minus 2 squared plus 9. A times 5 minus 2, there's a 3 squared plus a 9. So, and A times 9 plus 9 has to be equal to 0. Okay, that 9 started to look like an A. My A is going to have to be -1. So my final function for the demand as a function of the price would look like negative x minus 2 squared plus 9.